Hello, today I will talk about how to calculate the electric field due to a charged rod. This is similar to calculating the electric field due to a uniform ring. However, we only need to concentrate on one dimension at a time. So what I have here is a rod on a Cartesian plane, and I just put it on the x-axis, it doesn't matter. And it is uniformly charged with protons. It could also be uniformly charged with electrons. It doesn't matter. So, what we are given are these things. We are told that we need to look at this point at the origin, P. We are told that the total charge in the rod is Q, and that the rod has a uniform charge, so its two-dimensional linear charge, or one-dimensional linear charge density is lambda. And lambda is, because that's a linear charge density, it's charge per unit length. Okay, so what we need to do is define a bunch of just spatial definitions, really, from this rod so that we can mathematically calculate the electric field that this rod provides to P. So first of all, we could just say that the length of the rod is L. It doesn't matter really. We can just pretend that the rod is infinitely thin, by the way, so this dimension does not matter. We can say that the distance from P to the rod is A. And now what we need to do is pick an infinitely small subsection of L to evaluate the electric field of on P. Because the reason why we do this is the entire charged rod is providing an electrical field on point P. However, due to the fact that the distance is varying, this point right here is going to be giving P a stronger electric field than here, than here, than here, than here. So we need to break this up into infinitely small subsections. So we can break this up into an infinitely small subsection in terms of distance. We can call that dx. And just for mathematical sake, we need to define a distance horizontally from P to dx. And this could be anywhere. So we'll call this distance x. Okay, next, because we said that this rod is uniformly charged with protons, the electrical field it will be providing to point P will be pointing away from the rod. So I'll just draw it up here, but the electrical field will be in this direction. And that will be the vector for the electrical field. So we need to understand that the electrical field is changing because the rod has a length, it's not a point charge. So we need to create a relationship between the changing electrical field and the changing distance. So we can start step one by just defining the changing electrical field, and we can start just by defining the electrical field itself. So the electrical field in the x direction is just equal to the constant 9 times 10 to the 9th times the charge. This is a little q. It's really the same thing as big Q. So the constant times the charge over the distance squared. So for the distance, I will say x squared because it's in the x direction. And this is a vector in the I direction, or you could say in the x direction. So now what we're going to do, well, I'll make this I look more like an I. It has the I hat form because it's a vector. Because this charge Q is changing, because it's changing, essentially, with respect to the point P, we need to take the derivative of both sides. because the field is changing as a result. So that means the equation becomes, you can start out with this equation too, is that the changing electric field vector in the x direction is equal to the constant from Coulomb's expression times the changing charge over the distance squared. So now if you remember that the uniform linear charge density lambda, that's constant throughout. So the main trick is to convert this changing charge dq into a changing distance. So if dq, which is a charge, a changing charge, if we take our uniform charge density lambda, which is a charge per unit length, and multiply that by our changing length, so that would be dx, the infinitely small changing length we defined right here, we can substitute that in for dq because the lengths cancel and because it's uniform. So now for this equation, we can say that the changing electric field vector in the x direction, and also I just dropped the I from the vector notation, but you would essentially have to leave that in. I'll put it in at the end. So the changing electric field in the x direction is equal to k, substituting that expression in for dq, times the uniform linear charge density times the infinitely small changing length over the distance squared. Okay, so now what we're solving for is just the total electric field. So we're just solving for down here. We're just solving for this, and this is at point P. So in order to get from dE in the x direction to just E in the x direction, we need to integrate with calculus to sum up all the infinitely small changes in charge and distance. So if we integrate both sides, then we'll get the integral of d E vector in the x direction is going to be equal to the integral of k times the linear uniform charge density times dx over x squared. Now k and lambda are constants because this is just 9 times 10 to the 9th, and this is our constant uniform linear charge density, so it's the same throughout the entire rod. So we can pull those out of the integral. So we can say that this is now equal to k times lambda times 1 over x squared dx, which is the same thing as dx over x squared. So now what we can do is just integrate this, and when you integrate this you get the E electric field vector in the x direction is equal to the constant times lambda times the integral of 1 over x squared is negative 1 over x. And now we need to look at what our bounds are. Where does the rod start and where does it end in terms of our distances? Well, it starts right here. So from point P, that's just this distance A. Okay, so that is where it starts. So I could have put this down here. So for evaluating the integral that starts at A, and it ends right here. So that's a distance of A plus this distance L. So that's A plus L. So now when you plug this in, we can see that the electric field vector in the x direction is equal to the K constant times lambda times 1 over A, because we're just plugging those values, and well, it's 1 over A first because of the negative, but we're just plugging in these values from the calculus. So 1 over A minus 1 over L plus A. L plus A. Okay, and now if we remember that because lambda is a charge per unit length, it's really just the total charge over the length of the rod. So the charge density is the total charge, which was given to us as Q, over its length, L, which is right here. So if we plug that in for lambda, we now see that the electrical field vector in the x direction is equal to the constant of 9 times 10 to the 9th times its total charge over its total distance, or just its electrical charge density, times this right here, this expression from the calculus part. And if you simplify that just with algebra, you see that this just equals the constant times the total charge over A times L plus A. So essentially with this equation, if you have a point P and you know how far away it is from the rod, and you know how long the rod is, and you know its total charge, you can calculate the electric field at point P along a single dimension. Thank you very much.